Hi, everybody. Welcome back to Dave's Math Channel. This is my continuing feature on daily math problems, which I post every few days on the Facebook group Classical Mathematics. And the last one I posted, which I posted yesterday, is on random dice. I think the problem statement was a little bit confusing. I wasn't talking about random rolls of dice. I was actually talking about randomly configured dice, which is a little bit of a different problem. I don't know if you guys realize it, but standard dice, the opposite faces always add up to 7. And there's only, I think, one way to do that up to rotations and reflections. But for non-standard dice, you can actually have 15 possible configurations. The numbers on each face are completely random numbers from 1 to 6. The only requirement being that each of the numbers 1 through 6 is used on exactly one face. So anyway, here's the statement of the problem. So imagine we have one of these six-sided non-standard dice, and that the numbers on the faces are completely random, meaning that they can be in any one of these 15 configurations I just talked about with equal probability for each one. So then what I'm asking for is, first of all, the expected value of the sum of the products on opposite faces of a dice. And then I'm also asking for the standard deviation. Uh, I'll go into that if you don't know what that means. But standard deviation is a very common and very important topic in probability and statistics, so it's something worth knowing. So anyway, let's just show how to solve this problem. I think before I continue, I want to congratulate Wesley Suan. He was the guy who first solved this problem, and he got the answer right. And anyway, so let's just see how we do it. I wrote Mathematica code like I usually do to solve this problem. The first thing I did was I wrote code to list all 15 possible dice configurations, and they're listed on the bottom. I don't know if you can see this very clearly, but I have 15 lists. These are lists of pairs. And the lists are given with braces, and then each pair is given with an inner braces. So, for instance, the first configuration we have 1 comma 2 in braces, then 3 comma 4, then 5 comma 6. What that means is we have a die where the opposite faces are 1 and 2, numbered 1 and 2, numbered 3 and 4, numbered 5 and 6. And that's a non-standard dice. The only one of these that's standard is the last one, where 1 and 6 are opposite, 2 and 5 are opposite, and 3 and 4 are opposite. Every die you ever see will look like that. But nobody says we couldn't make dice that look like the other ones. So those are what the dice look like. And now to get their to answer the problem, we just have to calculate the sums of the products of the faces for each of these 15 dice. And I do this next, and you can see I get a list of 15 numbers here. These are just the sums of the products. And you can see they're not all the same. They range from, I believe, 28 at the smallest, and I think 44, is that right? Of the largest? Yeah. So they go up from 28 to 44. And if you calculate the mean, which you could do with just one command in Mathematica, there's a function called mean. But if you don't have Mathematica, you could just take the sum and divide by the number, which in this case is 15. So you'll get 35 if you do that. Some of these numbers is 525. I bet that by 15 you'll get 35. So that is the answer to the first part of this problem, the mean, the expected value of the sums of the products of the numbers on the opposite faces of the dice is 35. Note that the standard one, the sum of the products, is just 28, though. As a matter of fact, I think that's the minimum possible. So And then to get the standard deviation, there is another command in Mathematica called standard deviation. But there's sort of two ways you can define the standard deviation. There's with n and there's with n minus 1. For some reason or other, Mathematica uses the n minus 1 definition, which is not what I wanted here. So I did this by hand. So the first thing I did was I calculated the deviations for the mean of each of these 15 values of the sums of the products. And if it's positive, that just means that it's bigger than the mean, bigger than the expected value. And I think you can see that the first value, which is the biggest, 44, that's 9 bigger than the mean. And the last one is 28, is 7 below the mean. Uh, and now what you do if you want to calculate the standard deviation is sometimes called root mean square deviation. So what you have to do is you have to square these numbers, which I didn't do explicitly here. But if you square all the deviations, calculate their mean, and then take the square root, that gives you the standard deviation. So that was the next command I did. I took the square root of the mean of the standard deviation, squares of the standard deviations, and I get this exact expression 3 times the square root of 14 over 5. But we don't really care about an algebraic representation. We just want to get that approximately. And if you calculate approximately, you get approximately 5.1996 or about 5.2. So that's the answer. The mean is 35 and the standard deviation is approximately 5.2. So that's how you solve this problem. Pretty straightforward problem if you know what's going on. Anyway, that concludes my video for today. So thank you for watching. Long live math, and I'll see you guys next time. Bye.